Well, here we are. Welcome to the physics video lecture. Once again, physics 105A video lecture 7. We are moving right along. And let's remind ourselves where we were. So last time, we're always working right now with Newton's law, one degree of freedom, or one dimension, as we say. So mass times acceleration, force of position, velocity, and time. And we've worked through a couple of examples now. So we had F equals constant, which you could call a function of position, principally speaking. We had F equals F naught e to the minus alpha t. That was a force as a function of time. We had a couple of friction problems. mg minus b times v, v being x dot. And we had F equals mg minus a different constant b, b squared. And in taking the limiting cases of these two, we found that it was useful to understand something about the Taylor expansion, series expansions. So, and limits b goes to 0. That's what we're doing here. That's not so clean. Limits b goes to 0. So far, so good. Then, here I'll just number these things like we do. So, then we had Taylor expansions. And that's where we're going to pick up and do the discussion of friction forces. So let's go ahead and write out our Taylor series. F of x equals, I'll do it in the compact form. K equals 0 to infinity. Kth derivative at x0 times x minus, let's write that a little different. That'll make some room. It's the kth derivative at x0 divided by k factorial, and then x minus x0 to the kth power. So you can always just write out the first few terms of this, but if you need them all, you just have this compact form, right? The 0th derivative is just the function evaluated at x0, and then onward. And important to note that because you're taking the derivative at a particular point, these are all constants. Okay, these are all constants because they've been evaluated at a certain point. So what we want to do now is talk about the frictional force. So force of friction, so I'll just write friction of an object. And there are different types of friction. You guys may remember the friction that's proportional to the normal force when you were first learning mechanics. So how about if we just even list those? Frictional forces. And then we can talk about the kind where you've got an object here, M, say that's a tabletop, you want to drag it with some dragging force. There's the weight, there's the normal force, and then I use lowercase f for the friction. And then when we learn this, we often learn the law that F opposes the motion and it's equal to mu times m, where this is a coefficient of friction. So I'm mentioning this because that's what we've learned before. So that's one kind of frictional force. That's not the kind we're going to talk about right now. So it's possible that you learned about the frictional force in a fluid. So we'll call this the force of friction on an object moving through a fluid. Through a fluid. And if we're talking about a fluid, we can be talking about a gas or a liquid. Gas or liquid. And in this case, I'll first give examples. First one would be a pendulum. Okay. So you have a mass, a little sphere on the end of a string. And we could even have that little sphere of radius r. It's going to oscillate back and forth. And there's going to be friction due to the motion through the air, and that may be what brings it to a stop. What else will bring it to a stop? Perhaps there's a little bit of friction here where the string is attached to whatever it's attached to. But eventually this pendulum is certainly going to come to a stop. Okay, the force of friction. So we just have pendulum in air. And another example, this is more in line with the ones we've done, is a fall, just a falling object. And then, we've got, say it's a tennis ball, and we're going to drop it through the air. Then we have mg here, and then we have F. I'm just going to write F equals question mark right there. So what kind of a frictional force is that going to be? Unlike the static and unlike this friction force, there's actually a static force here. It takes a certain amount of pull to even get the thing to break loose. In a fluid, we can certainly say that when the object is motionless, there's no frictional force. So continuing this here, in a fluid, let F equal F of V. So this is the best example of a velocity-dependent friction force. And F of V equals 0 is equal to 0. Okay. Now the frictional force opposes the direction of motion. F, we can put a vector on there, but we know what we mean, right? So that it is a vector, but we're in one dimension. The force F opposes the direction of motion. Okay, opposes the direction of motion, and you could say it goes through the origin, or let's do this. Let's even draw a graph now. Experience shows, we already said V equals 0 is where we have F equals 0 and V equals 0. Experience shows that as you pick up speed, you feel more of a frictional force. Okay, if you're moving in a car, for instance, you feel that. If you're riding on a bicycle, you start feeling more wind buffeting you. So we're going to have an increasing function of V, and I'm just going to draw a curve, increasing function of V. And now let's expand that in a Taylor series. We're going to have F of V. It starts with 0, so we don't have a constant here, but we start with the first derivative, F prime of 0 times V plus 1/2 F double prime of 0 V squared 1/3 factorial third derivative b cubed. And you could keep going depending on how accurate you want that to be. But what we then do is restrict the speeds to slow speeds. And this really depends on the system, but in principle, if we make v small enough, then this term will dominate. Okay? For small values of v, we're going to do this a number of times in the course of the semester, but this time it's for this particular example. For small values, let me go ahead and do this. F of v equals, f prime of 0 times b. Now we're going to factor out 1 plus f double prime of 0, so over f prime of 0, and then we'll have a v. Again, that's where the v squared comes from, plus O of v squared. What that means is the next terms would be proportional to v squared, v cubed, and so forth, so they can all be subsumed under this v squared. And now we're going to analyze this expression here. What does it take for only this first term to, or for this first term to totally dominate? We require that all of this right here simply be much less than 1. Okay? Much less than 1. So that's the criterion, and you don't always know it in advance, but that's that criterion. And practically speaking, you say, okay, we're just going to restrict speeds to very, very slow speeds and do our calculation. Okay? But there's the actual criterion. So if they're this is much less than 1, then we can just have, I'll finish this up like so, then f of v can really be said to be just b times v for small speeds. Okay, so that f prime of 0, well, that's what we're going to rename b. Okay. So that's, so to speak, send that up a little higher. Okay, apparently not. I'll rewrite that. That's going to be the criterion. So you could say this is the whole thought process that justifies, so for slow speeds, for small v, f of v is equal to b times v. This is just the magnitude, v is a constant. But yeah, that's the thought process that justifies and explains a law like that. So that's what we mean. And now I'm going to give an example out of fluid mechanics. So in fluid mechanics, you have the force on a sphere. So force on a sphere, I'll just say capital R, that's its radius, moving in a fluid, which could, again, could be a gas or a liquid, with viscosity. With viscosity eta, a Greek letter for you. I'll just write it down. F is equal to 6 pi eta R times V. Okay, so that letter V would be the 6 pi eta R. Okay. And there's V, as you know, as before. Put a box around this. This is a Stokes Law, and has actually played a big role in physics, because if you guys remember the Milliken Experiment to determine the charge on an electron, actually the classic Milliken Experiment drops a little oil droplet with electric charge on it through air, falls through air, but air has a viscosity, and it's important to know what the speed and the radius is, and you have to make use of this formula here for the oil drop. So I'll even put this here, Milliken oil drop experiment, and you guys could look that up if you're interested. That's actually for the elementary charge of the electron. Okay. And then it'll be used for sedimentation rates and things like that as well. So let's have a look at this. We have, as before, we've worked with this thing already. You know, we have m dv dt is equal to mg minus b times v. There's an expression, an example of it. Positive direction down. And here's our, whatever it is, oil drop, mg b times v, the friction force opposing it. And of course, v terminal speed is equal to mg divided by b. So now we have an actual law, a linear law here, and we can get an interesting expression for the terminal speed, which is what I'm going to do next. I'll send this up. And in fact, in the Milliken experiment, you've got this thing free falling with its terminal speed, and then you dial in an electric field and make that same drop hover, and that gives you more information on it. So, I'm just going to analyze that expression for the terminal speed now, and we'll get a very useful little relation here. Good. So I can actually start right here. So we want to evaluate this expression here. So we have terminal speed is equal to mass g times this letter b here, which we now see is 6 pi eta r. Okay. Right, that is the coefficient. Now here's what we're going to do. I'm going to introduce a bunch of extra constants. So the mass is the density of the oil or whatever the object's made of, is the density times the volume. So for that mass, I'm going to write density and then 4/3 pi radius cubed. Okay. And then I have g. And in the denominator, I have that 6 pi eta r. So we're just going to simplify this. Okay, we've got pi is going to be gone. We have 4/18, which is going to be 2/9. So we've taken care of those numbers. And so what do we have here? Pi and pi, 4/18, 2/9, good. We have the density in g in the numerator, and the denominator we have eta, because r cubed over r is going to leave us with r squared. So I'll rewrite this, our terminal speed, and then we'll analyze it. This is the terminal speed even of those tiny oil droplets. So we have 2 density of our object g divided by 9 times eta, and then we have r squared. Okay, so does this make sense? Well, the density, say you have a little ball of oil versus a little ball of lead, makes sense that the more dense object is going to have a higher terminal speed. Gravitational acceleration is going to play the same role. The viscosity is here in the denominator, so less viscosity means a higher terminal speed, and we can even see that in the limit of the viscosity going to 0, and then we have true free fall, then the terminal speed goes to infinity, which is true free fall, right? It's unbounded. Now this dependence is also really interesting. This is actually why I did the whole thing, because an r squared dependence is a very strong dependence for the terminal speed. Imagine you have a drop exaggerated this big versus something that's just a fraction. Okay, from what I've drawn here, I'd say that's about 1/4 or 1/5 of the radius. We can even imagine 1/10. So you have 1/10, let's say this is 1/10, the radius. For the sake of argument, 1/10 squared is 1/100th. So the smaller drop falls much slower. And in fact, if you see these tiny drops, aerosolized mist, it just comes down really slow and pretty much just floats. And at some point, the terminal speed is so slow that the slightest breeze, the slightest updraft carries the aerosol, every which way. So there you have a nice example of a friction law. This one's really important in physics. It was originally used along with the Brownian motion concept to actually determine the size of atoms and molecules suspended in a fluid. So yeah, very important. That is the Stokes Law. Milliken Experiment, other things as well. How long it'll take for sediments to form, for a sediment to just fall out of a liquid, and so forth. So there you have it. Terminal speed, friction law, and to come back to this linear expression, what about the quadratic laws? Eventually I'll return to this graph here that I had erased. So now this linear law, I just drew this, not bad. Where is this thing linear? It's linear right here. So didn't quite get it right there. Right, it's tangent at the very bottom, so for small speeds, you've got the linear law. If you go beyond that, you've got a quadratic law, or some power in between even, or some sum of other powers. This law is actually very difficult to obtain from fluid mechanics, and in fact, it's even obtained when approximations are made in order to even solve the fluid mechanical equations. So anything beyond a linear law like this is more likely to be empirical. It's going to be empirical. You're going to have to do a lot of experiments to find out the particular range of speeds, and then it's going to depend on the shape and everything else. But this Stokes law for a sphere is very good, but it even breaks down when the speeds are too great. Okay, but the kind where something is just drifting down as a mist, it definitely holds true. Okay, let's consult the clock here. Good. That's a pretty thorough treatment. You're not likely to find this in your book, but it covers a lot of interesting territory. And it's not the last time that we have a velocity-dependent friction law. So, these things having been said, we're back to Newton's law and that list of force laws. This was just to really fill in the friction examples that we did. Okay. So back to Newton's law. So returning to mx second derivative f of x velocity time, and we've done a few of these now. We're going to do one of the most important. We now consider forces that are purely a function of position. Forces that are purely a function of position. So yeah, we could just replace this again, mdv dt equals f of x. But forces that are purely a function of position allow us, allow a whole new solution strategy. When we have a force that is simply a function of position, we can immediately define, define what we will come to know as a potential energy function. So let's define u of x is equal to the integral of f of x dx. We'll go ahead and put a little prime here as integration variable from some position A to x, and put the minus sign in front. So this is just, right now, we'll just introduce it formally as the potential energy function, comma, the potential energy. Now I'm going to do the following. There are a couple of different ways to introduce this, and I'll probably just do both of them. But we have this now, it's just a relation to force, an integral of it, and minus sign in front. Now let's go ahead and look at the differential equation. M d v dx times v is equal to f of x, and we can do our integration again. And if we do our integration here, or m v dv is equal to f of x dx, integrate v0 to v x0 x, and here we're going to have 1/2 m v squared minus 1/2 m v0 squared is equal to minus u of x plus u of x0, and that's one way to get our classic energy conservation. expression. So I'll have 1/2 mv squared plus u of x is equal to 1/2 mv0 squared plus u of x0. So that's one way, and you guys have seen energy conservation, perhaps in this form. Another way to do this is just to define our kinetic energy. So actually, we haven't introduced the kinetic energy yet in this way, but you could say, well, we've defined this as the kinetic energy. So having discovered this type of expression, we can also define, so next, define kinetic energy. And in classical mechanics, kinetic energy gets the letter T equals 1/2 mv squared. Okay. And then what we're going to do is this, and consider d dt of this t plus u as they've been defined up here. Okay, we have the potential energy, we have the kinetic energy. We're going to take its complete time derivative equals, well, since I have that right up there, I can just write, I've got 1/2 m 2v dv dt. Now the time derivative of u, I'll do in 2 steps. It's going to be du dx times dx dt. That's my chain rule. Okay. So let's see what we get. We get v. I can factor out a v, and then I have m dv dt. The 2's just canceled. And here I have du dx, but you guys have to remember the fundamental theorem of calculus. If I take the derivative of this integral with respect to x, it's the value of the integrand evaluated at x. I may even give a proof of that. If I had you here with me, I'd ask, do we need to see a proof of that? And somebody would say, yeah, show us proof. But for the moment, I'm just going to assume we know that. So the du dx is minus f of x, and the dx dt, of course, is v. So let me go ahead and finish that up right up here. So what we have is d dt t plus u is equal to, I can pull out the common factor v, and then I have m dv dt minus f of x. And what do we know about that? M dv dt equals f of x if Newton's law holds. So that is actually equal to 0. So that is 0. And what that means is this kinetic plus potential energy called the total mechanical energy, and it is conserved. So I'll just finish this right here. Mechanical energy leave the room here. That's 0. E equals t plus u is conserved, is constant in time. So that's conservation of energy. This is probably a great place. Now we have a few more minutes. This is good. Okay, so we have conservation of mechanical energy. And there are even a couple of other ways to do this. And in fact, I think I'll do this in another way. It's such an important point. When you have, now we can go through the whole thing. When you have a function that is only a function of position, this definition, you just define this thing, and what you get from that is that kinetic plus potential energy, the sum of the two is the mechanical energy, and that is conserved. So you get conservation of energy. So let's look at this one more time. And we have of course, we have great applications with this now. We get some really excellent problems. So I'm going to leave this up here and just work on this side of the board. Another way to look at this whole thing is begin with m x second derivative, multiply it by x first derivative equals f of x first derivative. Okay. Then you can again see this as d dt of 1/2 m x dot squared. Okay. Because when you take that derivative, 1/2 m2 cancels m x dot x second derivative. Okay. So you could just, essentially look at it and see what the antiderivative is. Okay. This one, however, you actually have to have this definition in place, because this is d dt of minus u of x. Okay. So you actually have to have this definition in place, namely you had an antiderivative here, so you had to have the antiderivative here. Oh no. Yeah. Because the minus u of x, when you take the derivative, you're going to get the f, and the chain rule is going to give you the dx dt. Okay. So then you say, okay, d dt 1/2 m x dot squared plus u of x equals 0. So yeah, that's essentially the same thing I did up there with this the integration I had up here before. So be that as it may, very important point. The thing is, now let's go ahead and look at this thing. So because this thing here is constant, and 1/2 m x dot squared plus u of x equals e equals constant. Okay. Now, Newton's law is a second order differential equation. This here is a differential equation, right? It has a derivative in here that we don't know. Okay. So 1/2 mx dot squared plus u of x equals e is a differential equation. It's a first order differential equation. So we've gone from a second order differential equation to a first order differential equation. You could say we're halfway there. And in fact, this thing is often really useful on its own. So back in physics, put the box in the wrong place. Back in physics 4A, you may have even just used this to solve for the velocity, which under circumstances is an important thing. Okay, so we have conservation of energy, and I'll just put this as a note for you. Note, second order differential equation, and here, first order differential equation. Now we have a lot to do with this. But this is a good place to stop for the day. So this progression that we did from here to here, that's one that I really recommend to you guys to just make really clear to yourself. You can just go, step, 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 and end up here. What we're going to do next time is investigate the general solution of this type of differential equation. And then the specific ones will be interesting as well. Good, so see you then.